Alright, rational zeros theorem. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas, El Paso, and an assistant professor at Doña Ana Community College. This is for Math 1508, a pre-calculus class at UTEP. Chapter 2, Polynomial and Rational Functions, comes from Larson's Pre-Calculus, 10th edition. Section 2.5, Zeros of Polynomial Functions, Part 1, I'm going to look at the rational zeros test. And in Part 2, my next lecture, I will be looking at complex zeros and Descartes' rule of signs. So let's start with some theorems. Here's a key tip for you. In math, if it has a fancy name, you should know it. If it's just called Theorem 7, it's important, but not quite as important as the ones that are called something like the fundamental theorem of algebra. This one's huge. If f of x is a polynomial of degree n, where n is greater than 0, then f has at least one 0 in the complex number system. Every polynomial has at least one 0 if we include complex numbers. But you see, it goes further. The linear factorization theorem says, if f of x is a polynomial of degree n, where n is greater than 0, then f has precisely n linear factors, where we could have complex numbers. But remember, real numbers are a subset of complex numbers, rational numbers are a subset of real numbers, and so on. So this says that if f of x has degree n, there are n linear factors. What do linear factors give us? Linear factors give us zeros. All right, we saw that in polynomial and synthetic division, the factor theorem, the remainder theorems. Those are some great theorems that come together and tell us polynomial of degree n, n factors, n roots, as long as we include complex numbers. So let's find all the zeros of some functions that are already in factored form. Finding zeros means replace f of x with 0. You want to find the roots, the x values, where the graph crosses the x-axis. So we're going to set y equal to 0. 0 equals x squared times x plus 3 times x squared minus 1. If we're multiplying things together to get 0, then either x squared is 0, or x plus 3 is 0, or x squared minus 1 is 0. We can solve each of these individually. If x squared equals 0, then x has to be 0. If x plus 3 equals 0, then x equals negative 3. If x squared minus 1 equals 0, we could either factor using difference of squares, or we could use a square root property that says add 1 to both sides, isolate the square part. If x squared equals 1, we take the square root of both sides. Anytime you choose to do the square root, you have to include the plus or minus. So x equals plus or minus 1. Those are my zeros. If f of x equals x plus 6 times x plus I times x minus I, I'm going to set each factor equal to 0. Each factor equal to 0 gives me zeros of x equals negative 6, x equals negative I, and x equals positive I. Remember, zeros, x-intercepts, roots, they all mean the same thing. If I say 1, I mean the other 2. That's all when y is equal to 0. And also remember, factors and zeros very closely related. That's from the factor theorem, right? Factors lead directly to zeros. So now we have the rational zero test. And the rational zero test is extremely helpful, actually, in finding zeros of polynomial functions. So if I have any polynomial with integer coefficients of degree n, every single rational zero of f is guaranteed to have the form p over q, where p over q has no common factors other than 1. So we wouldn't write 3/6, we would call it 1/2. All right, so all of my rational numbers are simplified, or in simplest form. The numerator is going to be a factor of the constant term. All right, p is a factor of a sub 0. And q is a factor of the leading coefficient. The leading coefficient factors give us our denominator. The constant factors give us our numerators. Let's take a look. Find all the rational zeros of f of x equals x cubed minus 7x minus 6. If I wanted to know all possible rational zeros, I would make the rational expression p over q. P, I want all factors of 6. So what numbers go into 6? 1, 2, 3, not 4, not 5, 6. And it could be plus or minus, we don't know. Divided by q. Q is all the factors of the leading coefficient of 1. I love it when the leading coefficient is 1. A plus or minus 1 in the denominator. So we have the possibilities of 1 over 1, 2 over 1, 3 over 1, 6 over 1, or negative 1, negative 2, negative 3, negative 6. And I write this collectively as plus or minus all of those options. So I do my divisions, but division by 1 is kind of boring. Don't worry, I'll give you a better example in a minute. So these are the possible rational zeros. If I want to actually find the rational zeros, I could use synthetic division, or I could just evaluate. These are my possibilities. Evaluate the function, see what you get. For me, I always start with ones. 1, it's a possibility, so I'm going to do synthetic division by 1. And when I do my synthetic division, my remainder is not 0. So I know that this is not going to be a 0 of the function because the remainder is not 0. So I move on. What's the next easiest value? Negative 1 is. So I do synthetic division, and I get a remainder of 0. So I know x equals negative 1 is a 0 of this function. Guaranteed, because my remainder is 0. So let's take this bottom line right here. Let's keep it in mind. I put it up here for our convenience. Now I can rewrite, right? F of x equals x cubed minus 7x minus 6. If x equals negative 1 is a 0, then x plus 1 is a factor. This was a cube, so my bottom line will be x squared minus x minus 6. And if you wanted to, you could keep using synthetic division, but this is something I can factor. X squared minus x minus 6 gives me the factors x minus 3 times x plus 2. I can now write this in completely factored notation. X cubed minus 7x minus 6 is x plus 1 times x minus 3 times x plus 2. And as always, the order of the factors does not matter. In multiplication, order doesn't matter, so whatever. The factors turn into zeros. X plus 1, factor, x equals negative 1. X minus 3, a factor, x equals 3. X plus 2, a factor, x equals negative 2. And I have my zeros. They all came from the possible rational zeros I had on the previous page. So let's put this all together on one page so we could see it happening. All possible rational zeros are the form p over q. P is a factor of the constant term, so all factors of 12, that's a bummer because there's a lot of them. 1, 2, 3, 4, 6, and 12. Divided by all the factors of the leading coefficient. Again, it's a 1. I like ones. And when I make all my fractions, it's just plus or minus 1, 2, 3, 4, 6, and 12. And just to shout out, this is poor notation. This is lazy man's notation. I'll show you what it really needs to be, I promise, before the end of this video. So again, I'm going to try 1. I always try 1 first because 1's the easiest. When I do synthetic division by 1, I end up with a remainder of 0. And I'm not going to lie to you, if I had to figure out if 1 was a 0, I would do 2 things before I chose synthetic division. First, I would put 1 in for x, because 1s are easy to evaluate. 1 to any power is 1. So that's 1 minus 9 plus 20 minus 12. 20 and 1 make 21. A negative 12 and a negative 9 make negative 21. So I know it's 0 without having to write down any work. This just confirms it. Once I know x equals 1 is a 0, I can write it in factored form, x minus 1. This was an x cubed, so my quotient will be x squared minus 8x plus 12. And this is a quadratic that I'm able to factor. 2 things that multiply to be 12 that have the same sign. We know that sign is negative, and they add to be 8. So it must be x minus 6 and x minus 2. Therefore, my zeros are 1, 6, and 2. Okay, so let's find all the rational zeros of the function 2x cubed plus 3x squared minus 1. So my numerator, p, all the factors of 1, still love 1s. My q, the denominator, all the factors of 2, that's 1 and 2. So I'm going to make all possible fractions. 1 over 1, 1 over 2. 1 over 1, 1 over 2. And they could be positive or negative. We don't know. So I try 1 because I always start with 1. I do not get a 0 remainder, so I know that this is not a factor. Not a 0. X equals negative 1. I try it in the original. Remember, that's 2x cubed, so I'll have 2x squared plus x minus 1 as a factor. I see that x equals negative 1 is a 0. 2x squared plus x minus 1. What would actually happen here? I would probably continue on. I know many people don't actually like factoring, especially if there's a leading term that's not 1 in front of your square. So what I might do, let's keep this going in green here, is I would take this bottom row, 2, 1, negative 1, and now I would try my next value. I'd probably try a positive 1/2. Bring down the 2, multiply, a half times 2 is 1, add, half times 2 is 1, add, and I know that x equals 1/2 is going to be a 0 as well. And if this was an x squared, right, because we started with x cubed, this is x squared, this will be x, this is 2x plus 2. Now that's not exactly the way I have it factored up here, but if I rewrite my factors in this form, I know that x plus 1 works because negative 1 went in. I know that x minus 1/2 works. Let's see if I can write a 2 here. And my third factor, of course, I did not leave room, so let's throw it out here. 2x plus 2. If I'm solving 2x plus 2 equals 0, I'm going to get x equals negative 1 also. Whether it's an x plus 1 or a 2x plus 2, that's just a constant different. And a constant, when you're setting it equal to 0, makes no difference. And so I probably would never test negative 1 again in what remains, but it turns out it's a repeated root here. It's never a bad idea. So let's find all real solutions of x to the 4th minus 13x squared minus 12x equals 0. The first thing I would always do is factor out the GCF. Notice that each term has an x involved, so I take the x out, factor, I'm left with x cubed minus 13x minus 12. So now we could focus on factoring the cubic by looking at possible rational zeros. All the factors of 12, 1, 2, 3, 4, 6, 12, divided by all the factors of x cubed, of 1, it's 1. I always start with 1 and negative 1 because they're the easiest with arithmetic. So when I divide by 1, I do not get a 0 remainder, so I know that that's not a 0. If I use negative 1, remember I'm looking at the cubic here, the cubic function, because I've factored out the x. I'll end up with a 0 remainder, so I factored out an x on the last slide. I found out x equals negative 1 is a 0, and if x equals negative 1 is a 0, let's do this in red. If x equals negative 1 is a 0, then when I add 1 to both sides, I get my factor. So x plus 1 is the factor that goes with the 0 of x equals negative 1. It was x to the 4th, I factored out an x. It was x to the 3rd, and I divided, so I have x squared minus x minus 12, and when I get it to something that I can factor, I factor it out. So all my real solutions, in completely factored form, x times x plus 1 times x minus 4 times x plus 3 equals 0, give me x equals 0, x equals negative 1, x equals 4, and x equals negative 3. Fourth degree polynomial, 4 zeros. Alright, so on this example, the first thing we're going to do is list all possible rational zeros. Then we're going to look at a sketch of the graph so that some of the zeros can be disregarded, and then we're going to find all the actual real zeros of f. Here we go. If f of x is negative 3x cubed plus 20x squared minus 36x plus 16, the possible rational zeros, the numerator, factors of 16, The denominator is factors of 3, so that's 1 and 3. So I make all possible combinations. I'll do 1 over 1, 2 over 1, 4 over 1, 8 over 1, 16 over 1, and then 1 over 3, 2 over 3, 4 over 3, 8 over 3, and 16 over 3. And you can see I wrote it in the lazy man's method here with the plus or minus, all of that in front. However, on WebAssign and possibly other online homework computer systems, you have to write these individually. So you would write 1, comma, negative 1, comma, 2, comma, negative 2, comma, 4, comma, negative 4. If your online homework system doesn't have a plus or minus button, you have to list these completely. One of the most frequent errors is you put the comma before you come out of the fraction. So if it looks like your answer is exactly the same as what the answer key is showing you, look for that, a comma that's in the denominator rather than after the fraction. Alright, so we found the possible rational zeros, and there's a lot of them. So I took a graphing calculator view of this graph. F of x equals negative 3x cubed plus 20x squared minus 36x plus 16, with a negative 5 to 5 window on x and a negative 10 to 10 window on y, scaling by 1. I see that a third degree polynomial has 3 zeros, and they're all positive. And I see all 3 of them in the interval from 0 to 5. So I know I don't have to check 16, I don't have to check 8, I don't have to check any of my negative values. Using this graph, I'm going to guess that 4 is one of mine. It looks like 2 works. And based on my list of possibilities, I'm guessing probably 2/3. So having the graph can help us narrow down possibilities. But just narrowing down possibilities, not enough. Actually check them, right? I guessed 2. Looks like 1. And so I used negative 3, 20, negative 36, and 16. Synthetic division, I got a remainder of 0. Once I get a remainder of 0, I don't have to go back to the original, right? This is the quadratic that remains. And it looked like 4 was also a 0. So I'll use just the terms from the quotient of the previous division, negative 3, 14, and negative 8. And I'll divide by my second guess of 4. Bring down the negative 3, multiply to go up and over. 4 times add to go straight down. 4 minus 12 is 2. Multiply to go up and over, and look at that, I was right. The graph gives us ideas. We must verify algebraically. Even a graphing calculator, it's only as exact as its operator. So verify algebraically that these are zeros. And what do I have left? This was a cube. So my bottom row is a squared. And this is what I use. So here I have a square. I use synthetic division. So I have a linear term. I've just factored. 2 is a 0, so x minus 2 is a factor. 4 is a 0, so x minus 4 is a factor. If negative 3x plus 2 is also a factor, then I know x equals a positive 2/3. Subtract 2, divide by negative 3, and I have my final 0.